In this screencast, we discuss the issue of windowing in the context of spectral estimation. The Wiener-Khinchin theorem states that the autocorrelation function and the power spectral density are Fourier pairs. Thus, theoretically, from a time series we can calculate the autocorrelation function and then apply the Fourier transform to obtain the power spectral density. However, in practice, the data sequence representing the time signal is finite. As a consequence, we can only obtain an estimate of the autocorrelation function on a limited number of lags. Based on this limited set of data samples, there are two equivalent ways to obtain the power spectral density by a non-parametric approach: the so-called direct way, or periodogram, and the indirect way, or collelogram. In practice, before applying either the direct or indirect method, we window the signal. Besides implicit windowing, due to the fact that we have a limited set of samples, we may also desire to window the signal prior to estimation of the power spectrum. Possible reasons are, for example, because we want to reduce the computational complexity, or because we wish to study a non-stationary signal in a time interval within which we can consider it stationary. Whatever the reason, the consequences of windowing are, first, that instead of the classic discrete Fourier transform, we use the n-point discrete Fourier transform, where n is the number of signal samples. Moreover, as we shall see, windowing causes loss of resolution in the spectral estimate and also spectral leakage. As a first instance, let us consider the simplest case of a rectangular window. In practice, if we have a signal x defined on n samples, in the time domain this is equivalent to interpret this signal as an originally infinite length signal, here in blue, multiplied by a window function, here in red, which is defined as once from 0 to n-1 and 0 elsewhere. After windowing, the second step is to take the discrete Fourier transform. Recalling the multiplication in the time domain is equivalent to convolution in the frequency domain, to obtain the Fourier transform of a windowed signal, we need to convolve the Fourier transform of the original signal by the transform of the window. For a rectangular window, the Fourier transform is given by a periodic sinc function. Now let's think for a moment intuitively what are the implications for the calculation of the power spectrum. We start from an underlying infinite length signal with a given spectrum, here in blue. Then we window the signal by a rectangular function whose Fourier transform is a sinc function. Finally, to obtain the power spectrum, we take the modulus squared of the convolution between the Fourier transform of the original signal and a sinc function. The result is that the obtained spectrum is a smoothed version of the original spectrum, with lower spectral resolution and the appearance of spurious peaks, a phenomenon commonly referred to as spectral leakage. The effects of the window are generally worse as the window length decreases. In this slide, we can see the Fourier transform of rectangular windows of different lengths. As it can be observed, when the length of the window considerably increases, its transform tends to a pulse, and thus the original spectrum could be in principle fully recovered. In fact, convolving any function by a delta pulse gives the function itself. When we look at finite length windows, the spectral resolution is determined by the width of the main lobe, while spectral leakage is determined by the side lobes. Increasing the window length causes a reduction of the width of the main lobe, and thus an increase in spectral resolution. By an approximate calculation, the width of the main lobe is proportional to 0.89 times 2 pi over n. By this formula, we can estimate the minimum frequency distance at which we can distinguish two spectral peaks, given a certain window length. If increasing the window length has benefits for spectral resolution, however, it does not have any influence on the height of the side lobes. To look at the effects of the window from a statistical point of view, we can calculate the expectation of the spectrum obtained from a windowed signal. This can be written as the expected value of the modulo squared of the convolution between the window transform and the signal transform. Since the window is deterministic, and the expected value of the square modulus of the signal is actually the power spectral density, we can rewrite this expectation as the true spectrum convolved by a periodic sink. By splitting the window function as the main lobe and the side lobes, we can rewrite this as the sum of two components. The first component, which is the convolution of the main lobe with the true spectrum, influences the resolution of the estimated spectrum, that is, the ability to distinguish between different spectral peaks. While the second component, which is the convolution of the true spectrum by the side lobe function, is responsible for spectral leakage, which is the appearance of spurious peaks at frequencies different from the true spectrum. As mentioned previously, while the length of the window has a direct effect on the resolution, the only way to reduce spectral leakage is to change the window function. Here we compare the Fourier transform of commonly used windows, such as the triangular and the Hanning window. As it can be observed, if we fix the window length, the triangular and Hanning windows provide a wider main lobe compared to the rectangular window, which means a lower spectral resolution. On the other hand, they provide lower side lobes, thus mitigating the problem of spectral leakage. To better understand the effects of windowing on spectral resolution and spectral leakage, we can look at an example. Here we simulate a sinusoidal signal composed by three distinct spectral peaks, one at 15 Hz, one at 20 Hz, and one at 40 Hz. Let us now estimate the power spectrum with rectangular windows of different lengths. When the window length is too short, the spectral resolution is not sufficient to distinguish the spectral peaks at 15 and 20 Hz. We could have actually known that in advance using the approximate estimation provided before. If we want to distinguish two frequencies f1 and f2, their difference must be larger than 0.89 times 2 pi over n. Inverting this formula for frequencies 15 and 20 Hz, we obtain that n must be at least 18 in order to distinguish the two frequencies. And in fact, when we look at the plot obtained for n equal to 20, we can indeed distinguish the two peaks. However, although with the rectangular window we can already distinguish the two spectral peaks with n equal 20, because of the high side lobes, we also see the appearance of ripple and of spurious peaks. As shown in the plot, some spurious peaks have higher amplitude compared to the real peak at 40 Hz, which could thus remain undetected. To understand this, it is useful to discuss the concept of equivalent bandwidth. Suppose we have a window of length n, and no matter the shape of the window, we assume that the maximum is in the middle of the window. Without loss of generality, we further assume the window to be centered in zero. Depending on the actual shape of the window, that is the value of the window function at each n, we can define the so-called equivalent length by normalizing the sum of all the values by the value in zero. Similarly, in the frequency, we can define the equivalent bandwidth as the integral of the window transform normalized by the value in zero. There exists a trade-off between time and bandwidth by which the product between the equivalent length and the equivalent bandwidth is constant. As a result, once we fix the window length, each window function has a determined bandwidth which is inversely proportional to the window length. In summary, when calculating the power spectrum from a limited set of samples, we can only obtain an estimate of the true spectrum. The original spectrum can only be recovered when the window length tends to infinity, which in practice is never the case. Looking at the window function in the frequency domain, we can extract some general properties. The spectral resolution of the obtained spectral estimates depends on the width of the main lobe, which is inversely proportional to the window length. On the other hand, the length of the window does not have any influence on the height of the side lobes, which determine spectral leakage. This can only be changed by changing the window function. In practice, a challenge in spectral estimation is to find the best compromise between resolution and leakage. Before concluding this screencast, we quickly review the effects of zero padding on the spectral estimate. When we use the endpoint DFT, we obtain a spectral estimate that is defined on n discrete frequency bins. When we apply zero padding, we virtually extend the signal length by adding zeros. And then calculating the DFT, we are now using a number of frequency bins L that is larger than before. However, it is important to note that zero padding does not increase spectral resolution, which is the ability to distinguish different spectral peaks in the obtained spectrum, but rather it calculates the spectrum at more interpolating frequency points, possibly improving its visualization. If, for example, we have a signal represented by a cosine wave with frequency 25 Hz, its true spectrum, shown here in blue, is a delta pulse at 25 Hz. However, suppose we have only 30 samples of this cosine signal. Then if we calculate the endpoint DFT, we obtain a discrete spectrum calculated at 30 frequency bins, which is here shown by the red squares. You may notice that with this 30-point DFT, we actually miss the peak at 25 Hz. If we apply zero padding and we extend the signal to a virtual length of 120 samples, we obtain the function in yellow. Thanks to zero padding, we can now see the peak even if we have a limited set of samples. However, there is also some ripples and spurious peaks at different frequencies. And if we further extend the signal length to 1500 samples, we obtain the function in purple, which almost looks like a continuous function. However, no matter how large the number of zeros we add, we can never recover the true spectrum. The only effect of further increasing zero padding is to walk at a smaller step on the purple function, which is the expected value of the spectrum obtained from a windowed signal, or, in other words, the true spectrum smoothed by a sinc function, at least for the case of a rectangular window. This concludes this screencast in which we discussed the consequences of windowing at zero padding on the estimation of the power spectral density. Thank you for listening.